Subscribe to the channel so you don't miss out on any of these videos. Imagine a galaxy so dark that even the most powerful telescopes in the world struggle to detect it. A galaxy almost invisible, composed almost entirely of something we can't even see or touch. This isn't a plot for a science fiction movie, it's real. These mysterious structures, known as ultra-dark galaxies, challenge almost everything we think we know about the universe. They're not just peculiar, they're transformative, hinting at forces and materials that defy conventional understanding. Why do these galaxies exist? What are they hiding? And most importantly, what do they tell us about the universe we live in? By the end of this video, you'll see why these ultra-dark galaxies are one of the greatest enigmas of modern astrophysics. When we think of galaxies, we usually picture radiant, star-filled wonders like the Milky Way. But ultra-dark galaxies are the complete opposite. They are dim, ghostly shadows in the cosmos, made up almost entirely of dark matter, a substance that, as baffling as it sounds, is invisible and interacts only through gravity. These galaxies have little to no stars, which is why they appear so faint. Instead, they seem to be colossal clumps of dark matter holding themselves together, almost as if the visible parts of a galaxy, the stars and gas, were stripped away, leaving only the dark skeleton behind. To understand ultra-dark galaxies, we first need to talk about dark matter. It's one of the most puzzling substances in the universe, making up about 27% of its total mass and energy. Despite being everywhere, dark matter doesn't emit light, absorb it, or reflect it. This makes it impossible to see directly, even with the most advanced technology. We only know it's there because of its gravitational pull on visible matter, like stars and gas. It's like watching leaves swirl in the wind. You can't see the wind itself, but you know it's there because of its effect on the leaves. Ultra-dark galaxies take this concept to an extreme. Discovered fairly recently, these galaxies are almost entirely made of dark matter. In fact, in some cases, dark matter accounts for up to 99.99% of their total mass. Think about that for a moment. These galaxies are nearly invisible, ghostly shadows in the vast darkness of space. They're out there, but you wouldn't know it just by looking. Astronomers have only been able to identify them through their gravitational effects on surrounding matter or the faint light they emit when gas occasionally collides and forms a few scattered stars. One of the most famous examples of an ultra-dark galaxy is Dragonfly 44, located in the Coma Cluster, a dense region of galaxies about 330 million light-years away from Earth. Discovered in 2015, Dragonfly 44 shocked scientists because it has the mass of the Milky Way, yet it produces less than 1% of the light. Imagine walking into a city the size of New York but finding only a handful of dim streetlights. That's the level of darkness we're talking about. But here's where it gets even stranger. The existence of ultra-dark galaxies isn't just a quirky cosmic oddity. It's a fundamental challenge to our understanding of how galaxies form and evolve. Conventional wisdom says galaxies form when gravity pulls together massive amounts of gas and dust, which eventually ignite to form stars. But ultra-dark galaxies seem to defy this process. They have all the mass of a regular galaxy, yet hardly any stars. Why? Scientists aren't entirely sure, but there are a few intriguing theories. One idea is that these galaxies formed in environments where the conditions for star formation were unfavorable. For example, they might lack the dense clouds of gas necessary to ignite star formation. Alternatively, something catastrophic could have happened early in their history, like a collision with another galaxy or an intense burst of radiation that stripped away their star-forming material. This would leave behind a dark galaxy, essentially a skeleton of dark matter. Another possibility is that ultra-dark galaxies are relics from the early universe, cosmic fossils that offer a glimpse into a time when the universe was still young. In the early stages of the cosmos, dark matter played a crucial role in shaping the structure of the universe. It acted as a kind of scaffolding, pulling in ordinary matter to form the first galaxies and stars. Ultra-dark galaxies might be remnants of this era, primordial structures that never evolved into fully fledged galaxies. If this is true, studying them could provide invaluable insights into the universe's origins. But here's where the mystery deepens. not all ultra-dark galaxies fit neatly into these explanations. Some, like Dragonfly 44, are found in galaxy clusters, dense regions teeming with other galaxies. Others, however, appear to be isolated, floating alone in the cosmic void. Why would a galaxy composed almost entirely of dark matter exist in such different environments? And why do they vary so much in size and structure? These questions remain unanswered, leaving astronomers scratching their heads. Ultra-dark galaxies also have profound implications for understanding dark matter itself. Dark matter remains one of the biggest mysteries in physics. We don't know what it's made of, how it interacts with regular matter, beyond gravity, or why it exists at all. Studying ultra-dark galaxies could help answer some of these questions. For example, if we can map the distribution of dark matter within these galaxies, we might learn more about its properties and behavior. Does it clump together like regular matter? Does it form structures? Or does it behave in ways we can't yet predict? But the challenges are immense. Observing ultra-dark galaxies is incredibly difficult because they emit so little light. Traditional telescopes struggle to detect them, which is why discoveries like Dragonfly 44 required innovative approaches. In this case, astronomers used a special telescope called the Dragonfly Telephoto Array, which is designed to detect faint, diffuse light. Even so, identifying and studying these galaxies is a painstaking process, often involving years of observation and analysis. What makes ultra-dark galaxies even more fascinating is their potential connection to other cosmic mysteries. For instance, they could be linked to the phenomenon of galaxy rotation curves, one of the first pieces of evidence for dark matter. In the 1970s, astronomers discovered that the outer edges of galaxies rotate faster than expected, a discrepancy attributed to the presence of unseen dark matter. Ultra-dark galaxies, composed almost entirely of this mysterious substance, could provide crucial clues to understanding this phenomenon. And then there's the question of what ultra-dark galaxies might reveal about the ultimate fate of the universe. Dark matter plays a central role in cosmic evolution, influencing everything from the formation of galaxies to the large-scale structure of the cosmos. If we can unravel the mysteries of ultra-dark galaxies, we might gain a deeper understanding of how the universe works and where it's headed. But for now, ultra-dark galaxies remain one of the universe's best-kept secrets. They are silent witnesses to cosmic history, shrouded in darkness and mystery. Each discovery raises new questions, pushing the boundaries of our knowledge and challenging us to rethink our place in the cosmos. The story of ultra-dark galaxies doesn't just end with their discovery. It's a gateway to rethinking what we know about the universe. The fact that such galaxies exist, composed almost entirely of dark matter, is like a glaring clue in a mystery novel that tells us we've missed something fundamental. These galaxies may hold the key to questions about the unseen forces shaping the cosmos, and their study could lead to breakthroughs in astrophysics, cosmology, and even fundamental physics. Let's dig deeper into what makes ultra-dark galaxies such a conundrum. One of the most intriguing aspects of these galaxies is their sheer diversity. While Dragonfly 44 became the poster child for ultra-dark galaxies due to its massive size and high concentration of dark matter, many smaller, dimmer ultra-dark galaxies have also been discovered. Some of these are barely held together, almost teetering on the edge of gravitational disintegration. Others seem oddly stable, as though the dark matter within them is organized in a way that's different from anything we've seen before. This diversity suggests that ultra-dark galaxies aren't a one-size-fits-all phenomenon. They might form in several different ways or be influenced by their environments in unexpected ways. Take, for instance, the smaller ultra-dark galaxies discovered in the Virgo cluster. Unlike Dragonfly 44, these galaxies have significantly less mass, but they still defy conventional expectations. They're held together by dark matter, yet they show no signs of substantial star formation. Why would dark matter dominate these galaxies in such a disproportionate way? Could these smaller ultra-dark galaxies represent an earlier stage of galactic evolution, or are they entirely different beasts altogether? These questions remain unanswered, adding yet another layer to the enigma. One theory gaining traction is that ultra-dark galaxies are products of galactic interactions or collisions. When galaxies pass too close to each other, the gravitational forces involved can strip away much of their gas and stars, leaving behind a dark matter-dominated remnant. This idea is supported by the fact that many ultra-dark galaxies are found in dense clusters, where such interactions are more likely to occur. But this explanation doesn't cover all cases, especially the isolated ultra-dark galaxies that appear to float alone in the void, far from the gravitational chaos of galaxy clusters. These isolated galaxies suggest there's another mechanism at work, one we don't yet understand. Another fascinating aspect of ultra-dark galaxies is how they challenge our theories of galaxy formation. For decades, the cold dark matter model has been the dominant framework for understanding how galaxies and large-scale structures form in the universe. This model predicts that dark matter acts as a gravitational scaffold, pulling in gas that eventually forms stars and galaxies. Ultra-dark galaxies seem to deviate from this model. If dark matter is so effective at pulling in gas, why do these galaxies lack stars? Are we missing something fundamental about how dark matter behaves, or is there an unknown process suppressing star formation in these galaxies? Some researchers speculate that feedback mechanisms could be to blame. For instance, intense bursts of radiation from nearby supernovae or active galactic nuclei could heat up the gas in a galaxy, preventing it from cooling and condensing into stars. Alternatively, the dark matter itself might play a more active role than we realize. There's even the possibility that dark matter could have properties beyond gravity, perhaps interacting with itself or with ordinary matter in subtle, as yet undetected ways. These possibilities make ultra-dark galaxies a kind of natural laboratory for testing new theories about dark matter. Adding to the intrigue, ultra-dark galaxies might not just tell us about dark matter, they could also offer clues about the elusive phenomenon of dark energy. Dark energy is the mysterious force driving the accelerated expansion of the universe, and its relationship with dark matter is one of the biggest questions in cosmology. Some scientists believe that studying how dark matter behaves in ultra-dark galaxies could shed light on this relationship. For instance, if we can map how dark matter is distributed within these galaxies, it might reveal whether dark energy influences dark matter in ways we don't yet understand. The tools used to study ultra-dark galaxies are also worth exploring because they highlight just how challenging these investigations are. Telescopes like the Dragonfly telephoto array represent a shift in how we approach astronomical observation. Unlike traditional telescopes, which are designed to focus on bright, high-resolution targets, the Dragonfly array is optimized for detecting faint, diffuse light. Its design was inspired by insect eyes, hence the name, Dragonfly, and it uses multiple small lenses to reduce glare and improve sensitivity. This innovative approach has allowed astronomers to spot objects like Dragonfly 44, which would otherwise remain invisible. But even with advanced tools, we've likely only scratched the surface of what's out there. Some researchers estimate that there could be thousands, perhaps millions, of ultra-dark galaxies scattered throughout the universe. Many of them are likely hiding in plain sight, their faint light blended into the background of more prominent galaxies and clusters. As our technology improves and our telescopes become more sensitive, we may uncover a vast, hidden population of these ghostly galaxies, each with its own story to tell. And it's not just about finding more ultra-dark galaxies. It's about what they might reveal about the cosmos as a whole. For instance, the distribution of ultra-dark galaxies could help us understand how dark matter is spread throughout the universe. Are these galaxies concentrated in certain regions, or are they evenly distributed? Do they cluster together, or are they more isolated? Answering these questions could provide critical insights into the large-scale structure of the universe and the role dark matter plays in shaping it. Ultra-dark galaxies also force us to confront deeper philosophical questions about the nature of existence. If most of the universe is made up of dark matter and dark energy, what does that mean for our understanding of reality? These galaxies are a stark reminder that the universe is not what it seems, that the luminous stars and galaxies we see in the night sky are just a tiny fraction of what's out there. The rest is hidden, waiting to be uncovered. Ultra-dark galaxies are more than just a curiosity. They're a challenge, a mystery, and an opportunity. They force us to rethink our assumptions, push the boundaries of our knowledge, and confront the unknown. Each discovery brings us one step closer to understanding the true nature of the universe, even as it reminds us how much we still don't know. The mystery of ultra-dark galaxies also underscores how interconnected different fields of astronomy and physics are. To unravel these enigmatic structures, scientists must draw on knowledge from a wide range of disciplines: cosmology, particle physics, astrophysics, and even quantum mechanics. Each piece of the puzzle adds depth to the overarching question of what these galaxies are, how they form, and why they are so vastly different from the more familiar types of galaxies in the universe. One critical area of research is the role of gravitational lensing in detecting and studying ultra-dark galaxies. Gravitational lensing occurs when a massive object, such as a galaxy cluster, bends the light of objects behind it. This effect can magnify and distort the light of faint galaxies, making them more visible to telescopes. For ultra-dark galaxies, gravitational lensing has been an invaluable tool. By analyzing how the light from background objects bends around a dark galaxy, astronomers can infer its mass distribution, even when the galaxy itself is almost invisible. This technique has provided some of the strongest evidence for the presence of dark matter in these galaxies and has allowed researchers to estimate the proportion of dark matter to ordinary matter within them. Another exciting avenue of exploration is the connection between ultra-dark galaxies and primordial black holes. Some scientists hypothesize that these galaxies could be tied to the mysterious population of black holes that may have formed shortly after the Big Bang. If primordial black holes exist, they could act as seeds for the formation of ultra-dark galaxies, drawing in dark matter and creating the gravitational framework for these ghostly structures. While this idea is still speculative, it highlights the potential for ultra-dark galaxies to shed light on some of the most fundamental questions about the early universe. Ultra-dark galaxies are also reshaping our understanding of galactic evolution. Traditional theories suggest that galaxies grow and evolve through a combination of star formation, mergers, and interactions with their surroundings. But ultra-dark galaxies challenge this narrative. If these galaxies lack stars, what drives their evolution? Are they relics of a bygone era, frozen in time, or do they undergo their own unique processes of change? Some researchers propose that ultra-dark galaxies could be the missing links in our understanding of how galaxies evolve, offering a glimpse into phases of development that are typically hidden from view. Moreover, the relationship between ultra-dark galaxies and galaxy clusters adds another layer of complexity. Many ultra-dark galaxies are found in dense clusters, where interactions between galaxies are frequent and intense. These environments could play a crucial role in shaping the properties of ultra-dark galaxies. For example, the gravitational forces within a cluster might strip a galaxy of its gas and stars, leaving behind a dark matter-dominated remnant. But this doesn't explain the existence of isolated ultra-dark galaxies, which appear to defy the influence of their surroundings. Understanding these differences could help scientists unravel the environmental factors that contribute to the formation and survival of ultra-dark galaxies. The discovery of ultra-dark galaxies has also reignited debates about the nature of dark matter itself. For decades, dark matter has been one of the most elusive components of the universe. We know it exists because of its gravitational effects, but its true nature remains a mystery. Is it composed of weakly interacting massive particles, WIMPs? Could it be made of axions, sterile neutrinos, or some other exotic particle? Or is our understanding of gravity fundamentally flawed, requiring a new theory like modified Newtonian dynamics, MOND, to explain the observations? Ultra-dark galaxies provide a unique testing ground for these ideas. By studying how dark matter behaves in these galaxies, scientists hope to gain insights into its properties and interactions. For instance, some researchers have proposed that dark matter might have self-interacting properties, meaning that dark matter particles could collide or interact with each other in ways that ordinary matter does not. If this is true, it could explain some of the unusual features of ultra-dark galaxies, such as their stability or the distribution of dark matter within them. Observations of these galaxies could help scientists determine whether self-interacting dark matter is a viable explanation, potentially revolutionizing our understanding of the cosmos. The implications of ultra-dark galaxies extend beyond the realm of astrophysics. They force us to confront the limitations of human perception and knowledge. These galaxies are essentially invisible to the naked eye, detectable only through their gravitational effects and faint emissions. They remind us that the universe is far more complex and mysterious than it appears, filled with phenomena that challenge our understanding of reality. This realization has profound philosophical implications, raising questions about the nature of existence and our place in the cosmos. As technology advances, our ability to study ultra-dark galaxies will continue to improve. Next-generation telescopes, such as the James Webb Space Telescope, JWST, and the Vera C. Rubin Observatory, are expected to play a pivotal role in uncovering more about these enigmatic structures. The JWST, with its incredible sensitivity to infrared light, could reveal details about the faint remnants of stars or gas within ultra-dark galaxies, providing new clues about their composition and history. Meanwhile, the Rubin Observatory's wide-field surveys could help identify more ultra-dark galaxies, increasing the sample size and allowing for more comprehensive studies. The study of ultra-dark galaxies is also paving the way for new theoretical frameworks. As scientists grapple with the data, they are forced to develop models that can account for the unique properties of these galaxies. These models often challenge existing paradigms, leading to fresh perspectives on everything from galaxy formation to the fundamental nature of dark matter. In this sense, ultra-dark galaxies are not just objects of curiosity, they're catalysts for scientific innovation, driving progress in our understanding of the universe. What makes ultra-dark galaxies so compelling is their ability to bridge the gap between the known and the unknown. They exist at the intersection of observable phenomena and theoretical speculation, offering a glimpse into the hidden mechanisms that govern the cosmos. By studying these galaxies, we're not just learning about dark matter or galactic evolution, we're uncovering the deeper principles that shape the universe itself. Perhaps the most exciting aspect of ultra-dark galaxies is the sense of possibility they evoke. Each new discovery opens up a world of questions, hinting at the vast, uncharted territories that remain to be explored. These galaxies remind us that science is an ongoing journey, driven by curiosity and the desire to understand. They inspire us to look deeper, think bigger, and never stop asking questions. As we continue to study ultra-dark galaxies, we're likely to encounter surprises that challenge our assumptions and reshape our understanding of the universe. These galaxies are a testament to the power of observation and the enduring mystery of the cosmos. They're a reminder that, no matter how much we learn, there will always be more to discover, hidden in the darkness, waiting for the light of understanding to shine. The potential for surprises within the study of ultra-dark galaxies is immense. As we refine our tools and methodologies, there's a growing sense that these enigmatic structures may hold secrets about not only their own formation but also the overarching story of the universe. One tantalizing question is whether ultra-dark galaxies are unique to specific cosmic epochs, or if they've existed throughout the history of the universe. If they are relics of an earlier time, they might serve as fossils from the dawn of cosmic structure formation, offering an unprecedented glimpse into the processes that shaped the first galaxies. Ultra-dark galaxies may also redefine how we classify and categorize galaxies in general. Traditional methods rely heavily on visible characteristics like size, shape, and brightness. But what happens when those features are absent, replaced by the gravitational signature of unseen matter? These galaxies challenge our taxonomy, urging us to think beyond the visible spectrum and reconsider what it means to be a galaxy. Could there be even stranger types of galactic systems that have so far evaded detection entirely? The study of ultra-dark galaxies forces us to ask these questions, pushing the boundaries of our imagination and our scientific frameworks. Another layer of mystery lies in the potential for ultra-dark galaxies to host exotic phenomena. For instance, some researchers speculate that these galaxies could be ideal environments for understanding the interplay between dark matter and baryonic matter under extreme conditions. Unlike typical galaxies, where stars dominate the dynamics, ultra-dark galaxies provide a cleaner laboratory for isolating the effects of dark matter. Observing how dark matter behaves in these unique settings could reveal unexpected properties or interactions, challenging existing models and opening the door to entirely new physics. The connection between ultra-dark galaxies and the cosmic web is another intriguing angle. The cosmic web is the large-scale structure of the universe, a vast network of filaments composed of dark matter, gas, and galaxies. Ultra-dark galaxies are often found near or within these filaments, suggesting that they may play a key role in the dynamics of the cosmic web. Understanding how these galaxies interact with the web could shed light on the distribution of dark matter across the universe and reveal patterns that have so far remained hidden. One of the most exciting aspects of studying ultra-dark galaxies is the possibility of discovering new physics. For decades, scientists have relied on the standard model of cosmology, which describes the universe as composed of dark energy, dark matter, and ordinary matter. While this model has been incredibly successful, it leaves many questions unanswered, questions that ultra-dark galaxies could help address. For example, if these galaxies exhibit unexpected behavior, it might indicate the need for modifications to our understanding of gravity or the introduction of new particle physics theories. The potential implications for dark energy are particularly intriguing. Dark energy is the mysterious force driving the accelerated expansion of the universe, and its nature remains one of the greatest unsolved mysteries in science. Some researchers hypothesize that studying the distribution and behavior of ultra-dark galaxies could provide indirect clues about dark energy. If these galaxies are influenced by dark energy in unique ways, they might serve as natural laboratories for probing its effects and refining our models of cosmic acceleration. Ultra-dark galaxies also have implications for the search for extraterrestrial intelligence, SETI. While these galaxies are unlikely to host traditional life forms due to their lack of stars, their unique properties could make them interesting targets for alternative SETI hypotheses. For instance, some theorists have speculated that advanced civilizations might harness dark matter for energy, or use ultra-dark galaxies as shelters from cosmic radiation. While such ideas are highly speculative, they highlight the imaginative possibilities that arise when we explore the unknown. As our observational capabilities continue to improve, the potential for breakthroughs grows exponentially. Instruments like the Square Kilometre Array, SKA, will revolutionize radio astronomy, allowing scientists to detect faint signals from the most distant and elusive galaxies. Meanwhile, advancements in machine learning and data analysis are enabling astronomers to sift through massive datasets more efficiently, uncovering patterns and anomalies that might have gone unnoticed before. These tools will be essential for identifying and studying ultra-dark galaxies on a larger scale. In the coming decades, we may also see the emergence of entirely new observational techniques tailored specifically to the study of ultra-dark galaxies. For example, researchers are exploring the use of gravitational wave detectors to study the interactions between dark matter structures. While this technology is still in its infancy, it could provide a revolutionary new way to observe the universe, revealing aspects of ultra-dark galaxies that are currently inaccessible. The mystery of ultra-dark galaxies isn't just a scientific puzzle, it's also a source of wonder and inspiration. These galaxies challenge our assumptions about what the universe is and how it works, reminding us that the cosmos is far stranger and more complex than we can imagine. They invite us to look beyond the obvious, to seek out the hidden and the obscure, and to embrace the uncertainty that drives discovery. In many ways, the study of ultra-dark galaxies embodies the essence of science itself, a relentless quest to understand the unknown, fueled by curiosity and a sense of awe. These galaxies are a testament to the power of human ingenuity, showing how far we've come in our ability to explore and understand the universe. Yet they also serve as a humbling reminder of how much we still have to learn. As we continue to investigate these enigmatic structures, one thing is certain: the journey will be as rewarding as the destination. The study of ultra-dark galaxies promises not only to deepen our understanding of the cosmos but also to inspire future generations of scientists, thinkers, and dreamers to push the boundaries of what's possible. In the darkness of these galaxies lies the light of discovery, waiting to be unveiled. The journey into the depths of ultra-dark galaxies represents an unending pursuit of knowledge, and the potential revelations hidden within them are boundless. These galaxies challenge our understanding of the universe's structure, its origins, and its fundamental nature, urging us to think beyond the limits of visible light and explore the shadowy dominion of dark matter. One particularly fascinating aspect of ultra-dark galaxies is their role in testing the limits of our current cosmological theories. The standard model of cosmology posits that dark matter and dark energy dominate the universe, yet their exact natures remain unknown. Ultra-dark galaxies offer a unique window into this unseen realm, as their existence and behavior may reveal inconsistencies or gaps in our models. For example, if the distribution of dark matter in these galaxies does not align with predictions, it could indicate a need for revised theories about the universe's evolution and composition. The study of ultra-dark galaxies also has significant implications for understanding galaxy formation and evolution. Traditional galaxies form through the collapse of gas and dust, igniting star formation that illuminates their structures. However, ultra-dark galaxies defy this narrative, as they exhibit minimal star formation despite their substantial dark matter halos. This anomaly suggests that factors like environmental conditions, gas composition, or dark matter density might play crucial roles in suppressing star formation. Investigating these factors could unveil entirely new mechanisms of galaxy formation, expanding our understanding of how the universe builds its vast cosmic structures. Moreover, ultra-dark galaxies challenge the conventional relationship between visible and dark matter. In most galaxies, visible matter, such as stars and gas, provides a rough proxy for the distribution of dark matter. However, in ultra-dark galaxies, this relationship breaks down, with dark matter vastly outstripping the amount of visible matter. This discrepancy raises questions about the processes that separate the two components, and whether there are universal principles governing their interaction. By studying these galaxies, we can probe the deeper connections between dark and visible matter, potentially uncovering hidden rules that govern their coexistence. The peculiar dynamics within ultra-dark galaxies also provide a testing ground for alternative theories of gravity. Modified Newtonian dynamics, MOND, and other non-standard gravitational theories propose that the effects attributed to dark matter could instead result from deviations in the laws of gravity at cosmic scales. Ultra-dark galaxies, with their extreme ratios of dark to visible matter, offer an ideal setting to test these theories. If observations of these galaxies fail to align with predictions based on conventional gravity, it could provide strong evidence for alternative explanations of galactic behavior. Another intriguing avenue of exploration is the potential connection between ultra-dark galaxies and primordial black holes. Some researchers hypothesize that these galaxies may harbor significant populations of such black holes, which could account for their unusual properties. Primordial black holes are hypothetical remnants from the early universe, thought to form shortly after the Big Bang. If they exist in large numbers within ultra-dark galaxies, they could provide insights into both the early universe and the enigmatic nature of dark matter, as some theories propose that dark matter itself could consist of these black holes. Ultra-dark galaxies also hold promise for advancing our understanding of baryonic physics under extreme conditions. Baryonic matter, the ordinary matter that makes up stars, planets, and us, behaves differently in the dark, star-poor environments of these galaxies. Studying the limited gas and dust within ultra-dark galaxies could reveal how baryonic matter interacts with dark matter in the absence of strong stellar influences. These insights might have implications for a wide range of astrophysical phenomena, from the behavior of intergalactic gas clouds to the formation of massive galaxy clusters. From a technological perspective, the study of ultra-dark galaxies is driving innovation in astronomical instrumentation and data analysis. Detecting these faint, elusive objects requires cutting-edge telescopes and imaging techniques capable of capturing the faintest traces of light. Instruments like the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescope, ELT, are poised to revolutionize our ability to study ultra-dark galaxies, offering unprecedented sensitivity and resolution. These technological advancements will not only illuminate the mysteries of ultra-dark galaxies but also enhance our ability to explore the universe as a whole. Furthermore, ultra-dark galaxies are likely to inspire new computational models and simulations. By incorporating the unique properties of these galaxies into cosmological simulations, researchers can test different scenarios for their formation and evolution. These models can then be compared to real-world observations, providing a feedback loop that refines our understanding of the universe. The interplay between observation and simulation is a hallmark of modern astrophysics, and ultra-dark galaxies represent a critical frontier in this ongoing effort. The cultural and philosophical implications of ultra-dark galaxies are equally profound. These mysterious entities remind us of the vastness and complexity of the cosmos, challenging our perception of the universe as a place of light and visibility. They serve as a metaphor for the limits of human understanding, urging us to embrace the unknown and seek answers in the face of uncertainty. In a broader sense, ultra-dark galaxies highlight the beauty of scientific inquiry, where even the darkest corners of the universe hold the promise of discovery. As we look to the future, the study of ultra-dark galaxies promises to remain a dynamic and evolving field. With each new observation, simulation, or theoretical insight, we move closer to unraveling their secrets and integrating their stories into the grand narrative of the cosmos. These galaxies are more than just objects of scientific curiosity. They are keys to understanding the universe itself, offering glimpses into its hidden architecture and the forces that shape it. In this era of discovery, ultra-dark galaxies stand as beacons of mystery, inviting us to explore the unseen and uncover the truths that lie in the shadows. They challenge us to think creatively, to question deeply, and to persevere in our quest for knowledge. And as we venture further into this uncharted territory, we can be certain that the mysteries of ultra-dark galaxies will continue to inspire wonder, curiosity, and a sense of awe for generations to come. The allure of ultra-dark galaxies lies not only in their role as cosmic mysteries but also in their potential to transform our understanding of the universe's most fundamental elements. These shadowy systems operate on the cutting edge of astronomical research, offering tantalizing glimpses into realms we are just beginning to comprehend. The next phase of discovery promises to deepen our knowledge while posing even more profound questions. One pressing mystery is the distribution of ultra-dark galaxies across the cosmos. Are they confined to certain regions, such as the outskirts of galaxy clusters or specific nodes of the cosmic web? Or are they more evenly spread throughout the universe, hiding in plain sight but eluding detection due to their faintness? Answering these questions requires not only advanced telescopes but also new strategies for identifying the gravitational fingerprints of these elusive structures. Gravitational lensing has proven to be one of the most effective tools in uncovering ultra-dark galaxies. This phenomenon occurs when a massive object, such as a galaxy or galaxy cluster, bends the light of more distant objects behind it. By carefully analyzing these distortions, astronomers can infer the presence and mass distribution of dark matter, including ultra-dark galaxies. The development of high-precision gravitational lensing techniques is therefore critical to expanding our understanding of these enigmatic systems. Additionally, the presence of ultra-dark galaxies within galaxy clusters presents intriguing opportunities for research. Clusters are among the most massive structures in the universe, composed of thousands of galaxies bound together by gravity and vast quantities of dark matter. Within these clusters, ultra-dark galaxies may play unique roles in the dynamics and evolution of the system. Their dark matter-dominated profiles could influence gravitational interactions, tidal forces, and even the cluster's overall stability. Ultra-dark galaxies also raise questions about the timeline of galaxy formation in the early universe. If they formed shortly after the Big Bang, their study could provide insights into the conditions of the primordial cosmos. For instance, did these galaxies fail to form stars due to a lack of available gas, or were they stripped of their baryonic material by violent interactions with other galaxies? Understanding these processes could reveal the environmental factors that shaped the evolution of the first cosmic structures. These questions naturally lead to the broader context of galaxy quenching, the process by which galaxies cease to form new stars. Ultra-dark galaxies represent an extreme case of quenching, with star formation almost entirely absent. Investigating their quiescence could help astronomers understand the mechanisms that shut down star formation in other galaxies, including larger and more luminous ones. This research has implications for fields ranging from stellar evolution to the life cycle of galaxies across cosmic time. The relationship between ultra-dark galaxies and intergalactic gas is another area ripe for exploration. The space between galaxies is filled with diffuse gas, which serves as a reservoir for star formation. In typical galaxies, this gas flows inward, fueling the birth of new stars. However, in ultra-dark galaxies, this process appears to be disrupted. By studying the interactions between ultra-dark galaxies and the surrounding gas, astronomers can gain insights into the physical conditions that govern the flow of matter across the universe. Moreover, the scarcity of baryonic matter in ultra-dark galaxies poses intriguing questions about their dark matter halos. Theoretical models suggest that the density and composition of a dark matter halo influence a galaxy's ability to retain gas and form stars. Ultra-dark galaxies, with their massive halos and minimal baryonic content, challenge these models, indicating that additional factors may be at play. These discrepancies could point to new physics or previously unrecognized properties of dark matter. The link between ultra-dark galaxies and the cosmic microwave background, CMB, also warrants investigation. The CMB is the faint afterglow of the Big Bang, providing a snapshot of the universe when it was just 380,000 years old. By correlating the locations of ultra-dark galaxies with features in the CMB, scientists could uncover clues about the distribution of dark matter during the universe's infancy. This research could refine our understanding of the early universe's structure and the processes that led to galaxy formation. As we delve deeper into these mysteries, it's worth considering the implications for the search for dark matter itself. Despite decades of research, the exact nature of dark matter remains elusive. Ultra-dark galaxies, as natural laboratories for studying dark matter, could provide the breakthroughs needed to solve this cosmic puzzle. Whether dark matter consists of weakly interacting massive particles, WIMPs, axions, or something entirely unexpected, these galaxies are uniquely positioned to reveal its secrets. The significance of ultra-dark galaxies extends beyond their immediate scientific value. They serve as reminders of the universe's capacity for surprise and its ability to defy our expectations. Just as their discovery has challenged conventional wisdom about galaxy formation, their continued study promises to push the boundaries of what we know, and what we think we know, about the cosmos. In the coming years, the combination of observational advancements, theoretical innovations, and interdisciplinary collaboration will undoubtedly lead to new insights about ultra-dark galaxies. As we uncover their secrets, we'll not only learn more about these peculiar systems, but also gain a deeper appreciation for the intricate and interconnected nature of the universe itself. The pursuit of knowledge about ultra-dark galaxies is a testament to humanity's enduring curiosity and ingenuity. These galaxies may be shrouded in darkness, but their study illuminates the path forward, guiding us toward a more complete understanding of the universe and our place within it. As we continue to unravel the mysteries of ultra-dark galaxies, their implications stretch across numerous fields of astrophysics, cosmology, and even particle physics. They are far more than mere oddities in the cosmic landscape. They are crucial pieces in the puzzle of understanding how the universe works at its most fundamental level. Each revelation about these enigmatic galaxies takes us one step closer to answering some of the most profound questions about the cosmos. One area of intense study is the potential role of ultra-dark galaxies in shaping the large-scale structure of the universe. The universe is organized into a vast cosmic web of galaxies, galaxy clusters, and intergalactic filaments, all interconnected by invisible strands of dark matter. Ultra-dark galaxies, with their massive dark matter halos and minimal visible matter, may play a significant role in defining the gravitational scaffolding of this web. Their gravitational influence could help bind together the structures of the cosmic web, even in regions where visible matter is sparse. Studying their distribution and density could therefore reveal new details about how dark matter governs the universe's large-scale architecture. Furthermore, the existence of ultra-dark galaxies may provide clues about the early stages of galaxy formation. In the standard model of cosmology, the first galaxies formed within dense regions of dark matter, where gas was able to cool and condense, leading to the formation of stars. Ultra-dark galaxies, however, seem to deviate from this process, as they lack the bright, star-filled cores typically associated with early galaxies. This raises questions about whether ultradark galaxies represent failed attempts at galaxy formation or if they are relics of an alternate evolutionary pathway. Either scenario would have profound implications for our understanding of how galaxies have evolved over the past 13.8 billion years. The lack of significant star formation in ultradark galaxies also highlights a broader mystery about the interplay between dark matter and baryonic matter. Why is it that some dark matter halos lead to vibrant, star-filled galaxies while others result in nearly invisible, ultradark galaxies? One hypothesis is that the initial conditions of the universe, such as the density and temperature of gas, might determine whether a galaxy becomes star-rich or star-poor. Alternatively, environmental factors like interactions with nearby galaxies or intense radiation from early quasars could strip gas from a forming galaxy, preventing star formation and leaving behind a dark matter-dominated remnant. Testing these hypotheses requires a combination of advanced simulations and high-resolution observations, both of which are rapidly improving with the advent of next-generation telescopes. The potential connection between ultradark galaxies and high-velocity clouds, HVCs, is another intriguing line of inquiry. HVCs are massive clouds of gas moving through the Milky Way's halo at speeds that suggest they are not gravitationally bound to our galaxy. Some researchers speculate that HVCs could be associated with small, dark matter-dominated halos, essentially ultra-dark galaxies in their earliest stages of formation. If this link can be confirmed, it would open up a new way of identifying and studying ultra-dark galaxies by tracing the movement and composition of these enigmatic gas clouds. Additionally, the study of ultra-dark galaxies offers a unique perspective on the nature of galaxy interactions. In galaxy clusters, interactions between galaxies often lead to dramatic events such as mergers, tidal disruptions, and bursts of star formation. Ultra-dark galaxies, however, seem to avoid these outcomes, maintaining their dark, star-poor profiles even in dense cluster environments. This resilience raises questions about their internal dynamics and the strength of their dark matter halos. Are ultra-dark galaxies more resistant to tidal forces than their brighter counterparts? Or do they simply occupy less active regions within clusters? Answering these questions could shed light on the role of dark matter in mediating galaxy interactions. From a technological standpoint, ultra-dark galaxies are driving innovations in observational astronomy. Their faintness and lack of bright stellar components make them incredibly difficult to detect using traditional methods. However, advances in radio astronomy, infrared imaging, and machine learning are helping astronomers identify these hidden galaxies with increasing precision. For example, radio telescopes can detect the faint emission of neutral hydrogen gas within ultra-dark galaxies, while infrared observatories like the James Webb Space Telescope can peer through cosmic dust to reveal their hidden structures. Machine learning algorithms, meanwhile, are being trained to analyze vast datasets from surveys like the Sloan Digital Sky Survey (SDSS) and identify patterns indicative of ultra-dark galaxies. These technological advancements are not only enhancing our ability to study ultra-dark galaxies but also benefiting the broader field of astronomy. Techniques developed to find these galaxies are being applied to other challenging problems, such as identifying rogue planets, studying the interstellar medium, and mapping the distribution of dark matter across the universe. In this way, the pursuit of ultra-dark galaxies is contributing to a deeper and more comprehensive understanding of the cosmos as a whole. The cultural and philosophical significance of ultra-dark galaxies cannot be overstated. They challenge our preconceptions about the nature of the universe, reminding us that much of reality lies beyond the reach of our senses. Their study embodies the spirit of scientific inquiry, driven by curiosity and the desire to explore the unknown. In a broader sense, ultra-dark galaxies serve as a metaphor for the unseen forces that shape our lives, from the gravitational pull of relationships to the invisible threads of history that connect us all. As research into ultra-dark galaxies progresses, it is likely to yield unexpected discoveries that will reshape our understanding of the universe. These galaxies, once thought to be anomalies, are proving to be integral components of the cosmic landscape, holding answers to questions we have yet to ask. Whether through revealing the nature of dark matter, refining our theories of galaxy formation, or uncovering new principles of physics, ultra-dark galaxies are poised to revolutionize our view of the cosmos. The study of ultra-dark galaxies is a testament to the power of human ingenuity and perseverance. These galaxies may be shrouded in darkness, but their exploration is bringing light to some of the universe's deepest mysteries. As we continue to probe their secrets, we are not only expanding our knowledge of the cosmos but also enriching our understanding of ourselves and our place in the vast, ever-unfolding story of existence. The story of ultra-dark galaxies does not end with their current discovery. Instead, it opens up a cascade of deeper questions about the universe and humanity's capacity to comprehend its complexities. As researchers refine their tools and techniques, the mysteries of these galaxies will likely lead to breakthroughs in areas far beyond their initial scope. They represent not just an astronomical curiosity, but a critical nexus where astrophysics, cosmology, and theoretical physics converge. One of the most tantalizing aspects of ultra-dark galaxies is their potential role as laboratories for testing the nature of dark matter. Current cosmological models suggest that dark matter makes up about 85% of the universe's total matter content, yet it remains invisible and detectable only through its gravitational effects. The massive halos of dark matter in ultra-dark galaxies provide an unparalleled opportunity to study this elusive substance in isolation. Unlike brighter galaxies, where the interplay between baryonic and dark matter can obscure certain dynamics, ultra-dark galaxies allow researchers to observe the effects of dark matter more directly. For example, by studying the motion of gas clouds or the weak gravitational lensing signals in these galaxies, scientists can refine models of dark matter's behavior. Does it cluster differently in ultra-dark galaxies compared to more typical galaxies? Could its interaction, or lack thereof, with baryonic matter reveal previously unknown properties? These questions could eventually lead to experimental constraints on the characteristics of dark matter particles, such as their mass or interaction cross-sections. Additionally, ultra-dark galaxies challenge our assumptions about the universe's large-scale structure. If they are more numerous than currently observed, they could significantly affect estimates of the universe's total mass and the distribution of dark matter. Ultra-dark galaxies might even influence calculations of the universe's expansion rate, adding another layer to the ongoing debate over discrepancies in measurements of the Hubble constant. By integrating ultra-dark galaxies into cosmological models, researchers may discover new solutions to these persistent problems. Another area where ultra-dark galaxies may play a key role is in understanding the intergalactic medium, IGM, the vast expanse of gas and dark matter that exists between galaxies. The IGM serves as both a reservoir and a conduit for material flowing into galaxies, yet its interaction with ultra-dark galaxies is poorly understood. Do these galaxies act as sinks, trapping gas and preventing it from fueling other galaxies? Or do they simply passively drift within the cosmic web? Answering this question could reveal new details about how galaxies influence their surroundings and shape the overall evolution of the universe. Ultra-dark galaxies also provide a unique perspective on cosmic feedback mechanisms, particularly those involving active galactic nuclei, AGN, and supernovae. In brighter galaxies, these energetic processes play a critical role in regulating star formation and redistributing gas and metals. However, in ultra-dark galaxies, the absence of significant star formation raises questions about whether these feedback processes are completely absent, or merely operate differently. Investigating these dynamics could yield insights into how feedback mechanisms vary across different types of galaxies and environments. From a more speculative standpoint, ultra-dark galaxies might even hold clues about the existence of alternative theories of gravity. While dark matter is the prevailing explanation for the discrepancies between observed and predicted galaxy dynamics, some researchers have proposed modifications to gravity as an alternative explanation. Ultra-dark galaxies, with their extreme dark matter content, could serve as testing grounds for these theories. If their behavior cannot be fully explained by current models of dark matter, it might point to new physics at play. The discovery of ultra-dark galaxies has also prompted a re-evaluation of galaxy classification systems. Traditional categories like spiral, elliptical, and irregular fail to account for the unique characteristics of ultra-dark galaxies. As a result, astronomers are developing new frameworks to incorporate these galaxies into the broader taxonomy of cosmic structures. This process not only broadens our understanding of galaxies as a whole but also highlights the need for flexibility in scientific classification systems as new discoveries emerge. One of the most exciting prospects for studying ultra-dark galaxies lies in upcoming technological advancements. Telescopes such as the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope are poised to revolutionize our ability to detect faint objects in the universe. These observatories will provide deeper, wider, and more detailed surveys of the sky, significantly increasing the chances of identifying ultra-dark galaxies. Combined with advancements in computational astrophysics and machine learning, these tools will allow astronomers to uncover patterns and relationships that were previously invisible. On a philosophical level, ultra-dark galaxies remind us of the vast unknowns that still surround us. Their discovery underscores the limits of human perception and the importance of indirect observation in science. Much like the early recognition of black holes or the cosmic microwave background, the study of ultra-dark galaxies challenges us to think beyond the visible and embrace the complexities of an unseen universe. Moreover, these galaxies resonate with the broader theme of cosmic humility. They highlight the fact that even in the most meticulously studied regions of space, hidden treasures await discovery. This realization not only fuels scientific curiosity, but also fosters a sense of wonder and interconnectedness. Ultra-dark galaxies are a testament to the layered and intricate nature of existence, reminding us that every shadow holds the potential for light. As research progresses, the story of ultra-dark galaxies will undoubtedly continue to evolve. Their study is not just about understanding a specific class of objects, but about addressing some of the most profound questions in science. What is the universe made of? How did it come to be? And what role do we, as observers, play in its unfolding narrative? These questions drive the exploration of ultra-dark galaxies, ensuring that their mysteries will remain a focal point of scientific inquiry for generations to come. The pursuit of knowledge about ultra-dark galaxies stands as a beacon of human resilience and ingenuity. It reflects our innate desire to explore, understand, and connect with the cosmos, even in the face of immense challenges. Through the lens of ultra-dark galaxies, we are reminded that the universe is not just a place we observe, it is a profound mystery that calls us to participate in its discovery. Ultra-dark galaxies also bring up an important consideration about the environments in which they exist. Their presence in galaxy clusters or isolated regions could provide crucial clues about how these enigmatic structures form. For example, some ultra-dark galaxies are found near massive galaxy clusters, which might suggest that their development is tied to the gravitational forces of larger cosmic entities. In these dense environments, interactions like tidal stripping, where the gravitational pull from a larger galaxy removes stars and gas, could leave behind a skeleton of dark matter, giving rise to ultra-dark galaxies. Alternatively, isolated ultra-dark galaxies may offer insights into processes that allow dark matter to dominate over baryonic matter in quieter cosmic settings. These isolated galaxies could have formed in regions with low-density gas, where star formation was stunted from the beginning. If this theory holds, ultra-dark galaxies could represent some of the most pristine conditions of the early universe, untouched by the chaotic processes that shaped their brighter counterparts. Studying their locations in relation to the cosmic web, the vast network of dark matter filaments connecting galaxies, could also yield valuable data. Ultra-dark galaxies may lie at unique points within this web, such as low-density voids or intersections of filaments. Mapping their positions could help astronomers refine our understanding of how dark matter shapes the large-scale structure of the universe. Furthermore, these studies might reveal whether ultra-dark galaxies are relics of the past, frozen in time, or dynamic systems that continue to evolve in surprising ways. One particularly intriguing avenue of research involves the idea that ultra-dark galaxies could host ancient populations of stars, fossils of the first stellar generations. While these galaxies appear to have very little visible matter, the stars they do contain could belong to extremely old populations, dating back to the earliest epochs of cosmic history. These stars, known as population 3 stars, are believed to have been composed almost entirely of hydrogen and helium, the primordial elements produced after the Big Bang. Detecting remnants of such stars in ultra-dark galaxies would be a groundbreaking discovery, offering a direct glimpse into the universe's infancy. Another layer of mystery lies in the role of black holes within ultra-dark galaxies. In traditional galaxies, supermassive black holes at their centers are thought to play a key role in shaping galaxy evolution, often regulating star formation through powerful jets and winds. However, in ultra-dark galaxies, the absence of significant star formation raises questions about whether these galaxies also host central black holes. If they do, studying the interaction between these black holes and their predominantly dark matter environments could reveal novel insights into black hole growth and activity in extreme conditions. Conversely, if ultra-dark galaxies lack black holes entirely, it might suggest that certain conditions, like a critical threshold of baryonic matter, are required for black hole formation. Additionally, ultra-dark galaxies might challenge our understanding of galaxy mergers and interactions. Galaxies frequently collide and merge throughout the universe's history, triggering bursts of star formation and shaping their overall structure. However, in ultra-dark galaxies, such interactions may proceed in ways that defy current models. Their predominantly dark matter composition could lead to unique merger dynamics, where the visible components play a negligible role. Observing these interactions could provide an unparalleled opportunity to study dark matter physics in action, offering real-time tests of theoretical predictions. From a technological perspective, the study of ultra-dark galaxies pushes the boundaries of observational astronomy. Detecting such faint objects requires the most advanced instruments and techniques available. The use of adaptive optics, which compensates for the blurring effects of Earth's atmosphere, has been critical in resolving ultra-dark galaxies. Similarly, space-based telescopes like the Hubble Space Telescope and the James Webb Space Telescope have been pivotal in identifying these elusive objects. As technology continues to evolve, next-generation telescopes will provide even more detailed views of ultra-dark galaxies, enabling astronomers to map their structures, measure their dynamics, and trace their evolution with unprecedented precision. The significance of ultra-dark galaxies extends beyond their role as scientific curiosities. They challenge the way we think about the universe and our place within it. In a cosmos filled with luminous galaxies, shining stars, and brilliant nebulae, ultra-dark galaxies are a stark reminder of the unseen. They represent the vast, hidden framework of dark matter that underpins the universe, shaping its structure while remaining invisible to the human eye. This duality between light and darkness, visibility and invisibility, forces us to confront the limitations of our perception and the necessity of scientific inquiry. Moreover, the study of ultra-dark galaxies embodies the spirit of exploration and curiosity that drives humanity's pursuit of knowledge. These galaxies, though faint and elusive, have captured the imagination of scientists and the public alike. They invite us to look deeper into the cosmos, to question what we know, and to embrace the unknown. In doing so, ultra-dark galaxies become not just objects of study but symbols of the infinite possibilities that the universe holds. As we continue to uncover the secrets of ultra-dark galaxies, we are reminded that the universe is far more complex and enigmatic than we can currently comprehend. Each discovery opens new doors, revealing layers of mystery that challenge our understanding and inspire our curiosity. Ultra-dark galaxies are not merely isolated phenomena. They are part of a larger narrative that connects us to the cosmos and its infinite wonders. Their study is a testament to the power of human ingenuity and the enduring quest to unravel the mysteries of existence. The true significance of ultra-dark galaxies lies not just in what they are but in what they represent, a frontier of discovery that beckons us to venture into the unknown and expand the horizons of human understanding. The deeper we delve into the mystery of ultra-dark galaxies, the more profound the questions become. One particularly compelling aspect of these galaxies is their relationship to dark matter itself. Dark matter, the elusive substance that makes up approximately 85% of the universe's total mass, remains one of the greatest enigmas in modern science. Ultra-dark galaxies, composed predominantly of this substance, offer an unprecedented opportunity to study its properties in a natural laboratory. For decades, scientists have sought to understand the nature of dark matter, whether it is made up of weakly interacting massive particles, WIMPs, axions, or something entirely unknown. Ultra-dark galaxies provide a unique testing ground for these theories. Their high dark matter to baryonic matter ratio allows researchers to isolate the effects of dark matter more clearly than in conventional galaxies, where the influence of visible matter complicates the analysis. By studying the motion of stars or gas within ultra-dark galaxies, astronomers can infer the gravitational influence of dark matter and test competing hypotheses about its composition and behavior. One key question is whether dark matter interacts with itself or with normal matter in ways other than through gravity. If dark matter particles experience some form of self-interaction, whether through collisions or other forces, it could leave observable imprints on the structure and dynamics of ultra-dark galaxies. For instance, self-interacting dark matter might create central cores of uniform density, as opposed to the steep density profiles predicted by simpler models. Detailed observations of ultra-dark galaxies could provide the first direct evidence of such interactions, potentially reshaping our understanding of dark matter physics. Additionally, the unique environments of ultra-dark galaxies may offer insights into how dark matter clumps together on small scales. Current simulations of the universe's evolution, based on the standard model of cosmology, predict a hierarchical structure where dark matter forms dense halos of varying sizes, from massive galaxy clusters to tiny subhalos. Ultra-dark galaxies might represent the smallest observable halos, giving us a glimpse into the lower limits of dark matter clustering. Their discovery and characterization could help refine these simulations, improving our ability to predict the distribution of dark matter across the cosmos. The study of ultra-dark galaxies also intersects with efforts to detect dark matter directly. Ground-based experiments like XCNONNT and space missions like the upcoming Euclid telescope aim to capture signals from dark matter particles or map their distribution. Ultra-dark galaxies could provide valuable targets for these missions, as their high dark matter content increases the likelihood of detecting a signal. For example, if dark matter particles occasionally annihilate or decay, they might produce gamma rays or other forms of radiation that could be detected in these galaxies. Pinpointing such emissions would not only confirm the existence of dark matter but also reveal its fundamental properties. Beyond their implications for dark matter research, ultra-dark galaxies challenge our broader understanding of galaxy formation and evolution. In conventional models, galaxies form through the cooling and condensation of gas within dark matter halos, leading to bursts of star formation and the growth of massive stellar populations. Ultra-dark galaxies defy this narrative, existing in a state of arrested development where star formation is either minimal or entirely absent. This discrepancy raises important questions. What factors prevent gas from condensing and forming stars in these galaxies? Could feedback processes, such as energy injection from supernovae or active galactic nuclei, play a role? Or do ultra-dark galaxies form in environments with inherently low gas densities, stifling their ability to grow? The answers to these questions may lie in the interplay between dark matter and baryonic matter during the earliest stages of galaxy formation. Ultra-dark galaxies could represent a missing link in our understanding of how galaxies emerge from the primordial soup of the early universe. By studying their chemical composition, astronomers might uncover traces of the conditions that prevailed shortly after the Big Bang, shedding light on the processes that shaped the universe's first structures. Moreover, ultra-dark galaxies could hold clues about the mysterious phenomenon of reionization. During the universe's first billion years, intense radiation from the first stars and galaxies ionized the surrounding gas, transforming the cosmos from an opaque state to the transparent one we see today. However, the exact sources of this reionizing radiation remain unclear. If ultra-dark galaxies contain remnants of ancient star-forming activity, they could provide a window into this critical epoch, helping us understand how the universe transitioned from darkness to light. Intriguingly, some ultra-dark galaxies may also harbor enigmatic features like globular clusters, dense groups of stars that orbit the galaxy's center. These clusters, if present, could serve as relics of a bygone era of star formation, offering valuable insights into the galaxy's history. Analyzing the ages, compositions, and motions of these clusters could reveal whether they formed in situ or were captured during interactions with other galaxies. Either scenario would have profound implications for our understanding of ultra-dark galaxies' origins. In addition to their scientific significance, ultra-dark galaxies evoke a sense of wonder and mystery that resonates deeply with our innate curiosity about the cosmos. They challenge us to look beyond the familiar, to question what we know, and to explore the unseen. Their existence reminds us that the universe is far richer and more complex than our current models suggest, filled with phenomena that defy easy explanation. In this sense, ultra-dark galaxies are not just objects of study but symbols of the boundless potential of discovery. As we continue to investigate these enigmatic galaxies, we are likely to uncover even more surprises. The study of ultra-dark galaxies is still in its infancy, and each new observation has the potential to revolutionize our understanding of the universe. Whether they hold the key to unlocking the mysteries of dark matter, the secrets of galaxy formation, or the story of the early universe, one thing is certain: ultra-dark galaxies will remain a focal point of astronomical research for years to come. The journey to understand ultra-dark galaxies is a testament to humanity's enduring quest for knowledge. It is a journey that pushes the boundaries of what we know, challenges our assumptions, and inspires us to look deeper into the cosmos. In their silent, shadowy presence, ultra-dark galaxies whisper of a universe that is far more intricate and awe-inspiring than we can imagine, a universe waiting to be explored. As we continue to delve deeper into the mysteries of ultra-dark galaxies, it becomes evident that their study is not merely an academic pursuit. It holds the potential to reshape fundamental aspects of physics and cosmology. One particularly fascinating avenue of research revolves around the relationship between dark matter and galaxy formation. While conventional galaxies are thought to form through the gradual accumulation of gas within a dark matter halo, the ultra-dark galaxies reveal an entirely different scenario. Their lack of visible stars and near-complete dominance of dark matter challenges existing models, suggesting that the process by which galaxies form in these environments might be fundamentally different from our previous understanding. One possibility is that ultra-dark galaxies formed under unique conditions in the early universe. In these environments, the influence of dark matter could have been so overwhelming that it suppressed the formation of stars, either by preventing gas from collapsing under its own gravity, or by hindering the cooling process necessary for star formation. The dynamics of these galaxies might not fit neatly within our current models of hierarchical galaxy formation, which suggests that smaller structures first formed and later merged to create larger galaxies. Instead, ultra-dark galaxies might represent an extreme or unusual case, a kind of failed galaxy that never fully evolved. This raises another intriguing question: how did ultra-dark galaxies manage to survive despite their lack of stars? Given that dark matter does not interact electromagnetically, it doesn't radiate or emit light, making it invisible to telescopes that detect visible, ultraviolet, or infrared light. This gives ultra-dark galaxies a unique and almost ghostly quality. Being composed almost entirely of dark matter means they are incredibly hard to detect and study. However, their gravitational effects on nearby galaxies, their distorted light, and their interactions with other cosmic structures are often the only clues astronomers have that they exist at all. These gravitational effects can reveal a wealth of information about the dark matter halos that envelop these galaxies. Interestingly, ultra-dark galaxies may also have implications for the study of galaxy clusters. Galaxy clusters are large, gravitationally bound groups of galaxies that represent some of the most massive structures in the universe. Dark matter plays a crucial role in the formation and evolution of galaxy clusters, with the distribution of dark matter within these clusters influencing the motion and behavior of the galaxies within them. By studying ultra-dark galaxies that reside at the edges of or within these clusters, astronomers can gain insight into the role that dark matter plays in cluster dynamics, potentially shedding light on the fundamental forces that govern large-scale structures in the universe. Moreover, ultra-dark galaxies are beginning to be considered as potential laboratories for studying the expansion of the universe itself. The study of how galaxies behave and evolve in dark matter-dominated environments can inform our understanding of cosmic acceleration, the phenomenon responsible for the accelerated expansion of the universe. By understanding how these ultra-dark galaxies interact with their surroundings, and by examining their redshift and motion relative to distant objects, astronomers can refine measurements of the universe's expansion rate, a process known as the Hubble constant. This, in turn, can help resolve ongoing debates in cosmology regarding the precise rate at which the universe is expanding, an issue that has proven to be one of the most contentious in modern science. Another compelling aspect of ultra-dark galaxies lies in their potential to unlock the secrets of the missing baryons problem. Baryons are the particles, protons and neutrons, that make up the visible matter in the universe, and they account for only a small fraction of the total matter in the cosmos. The majority of matter in the universe is composed of dark matter, but a significant amount of ordinary matter, or baryons, appears to be missing. Some scientists hypothesize that these missing baryons might be hiding in dark matter-dominated environments, such as ultra-dark galaxies. If this hypothesis proves correct, the discovery of baryons within ultra-dark galaxies could lead to a breakthrough in our understanding of the universe's overall composition and help answer a key question in astrophysics: where are all the baryons? Ultra-dark galaxies also raise fascinating questions about the evolution of life and the conditions necessary for habitability. Conventional galaxies are thought to harbor the necessary conditions for life: planets, stars, and an environment conducive to chemical reactions. However, in ultra-dark galaxies, the lack of stars or active star formation suggests that these environments are inhospitable for the kind of life we know. This raises the question: what conditions are truly necessary for life, and how might life emerge in environments far different from our own? Could life exist in dark matter-dominated galaxies, where the typical sources of energy, such as starlight, are absent? One possibility is that life, if it were to emerge in such an environment, might not rely on the same biochemical processes we are familiar with. Rather than relying on photons from stars, life in ultra-dark galaxies might use other forms of energy, perhaps harnessing dark matter in ways we cannot yet comprehend. This notion leads to fascinating speculative ideas about the potential for extraterrestrial life in the most unexpected corners of the universe, challenging our preconceived notions about the conditions that are necessary for life to exist. The implications of ultra-dark galaxies extend beyond the realm of theoretical astrophysics and cosmology, touching on fundamental questions about the nature of reality itself. These galaxies, formed from the invisible and the unknown, push the boundaries of what we can perceive and understand. The discovery of these galaxies forces us to confront the limits of our knowledge and the tools we use to explore the cosmos. We are only just beginning to uncover their secrets, and every observation provides new challenges and possibilities. Ultimately, ultra-dark galaxies represent one of the greatest frontiers of modern astronomy. They invite us to question everything we thought we knew about the universe, offering a glimpse into a cosmos that is far stranger and more complex than we could have imagined. As our observational techniques improve and our understanding of dark matter continues to evolve, we will undoubtedly learn more about these elusive structures, and in doing so, we may unlock some of the deepest mysteries of the universe. With each new discovery, we move closer to understanding the very fabric of reality. Ultra-dark galaxies, with their strange and mysterious nature, hold the potential to rewrite the laws of physics and open new doors to the unknown. Their study may eventually lead to breakthroughs that redefine our understanding of the cosmos and our place within it. As we continue to explore the universe, one thing is certain: the journey to understand ultra-dark galaxies will be one of the most exciting and rewarding chapters in the history of science. As the study of ultra-dark galaxies advances, new technologies and more powerful telescopes will allow scientists to uncover even deeper insights into these enigmatic structures. With tools like the James Webb Space Telescope and the upcoming Vera C. Rubin Observatory, astronomers will have access to a level of detail previously unimaginable. These advancements in observational technology will not only help us detect ultra-dark galaxies more efficiently, but also provide high-resolution data that can shed light on the very nature of dark matter itself. One of the most exciting prospects in this area of research is the possibility of detecting dark matter stars, or other exotic objects within ultra-dark galaxies. While conventional stars are composed of regular matter and shine due to nuclear fusion in their cores, dark matter does not interact with light in the same way. However, dark matter particles could potentially clump together in a way that forms dense objects with unique properties, such as dark matter stars, that might be detectable through gravitational effects or through the subtle bending of light. These hypothetical objects could open entirely new avenues of study and challenge our understanding of what constitutes a star. Additionally, ultra-dark galaxies might hold the key to solving one of the most pressing mysteries in cosmology: the nature of dark energy. Dark energy is the mysterious force driving the accelerated expansion of the universe, and its properties remain largely unknown. However, by studying how ultra-dark galaxies behave and interact with other cosmic structures, scientists may be able to detect subtle clues about the influence of dark energy in these environments. In particular, the distribution and motion of ultra-dark galaxies within galaxy clusters could provide crucial information about the ways in which dark energy affects large-scale cosmic structures, offering us a glimpse into the very fabric of the universe itself. In tandem with these new discoveries, ultra-dark galaxies also raise important questions about the evolution of the universe as a whole. If these galaxies formed under conditions that differ significantly from conventional galaxies, this could have profound implications for our understanding of cosmic history. It could suggest that the universe went through periods of rapid change or even failed galaxy formation in certain regions, leading to the creation of ultra-dark galaxies that never fully developed into the rich, star-filled structures we typically observe. These insights could offer a new perspective on the timeline of the universe, challenging the idea of a steady, predictable progression and instead highlighting the dynamic, sometimes chaotic nature of cosmic evolution. Furthermore, the study of ultra-dark galaxies could provide new clues about the initial conditions of the universe itself. The process by which galaxies form is tied to the distribution of matter and energy in the early universe, and by studying ultra-dark galaxies, we may learn more about the conditions that prevailed in the first few moments after the Big Bang. This could help us refine our models of the early universe, improving our understanding of how cosmic structures emerged from the primordial soup of particles and radiation that filled the universe during its infancy. Another interesting angle is how ultra-dark galaxies might relate to the so-called dark sector of the universe. Dark matter and dark energy are often grouped together as part of this mysterious sector, but there could be other forms of exotic matter or energy that contribute to the overall makeup of the universe. Ultra-dark galaxies might be a unique manifestation of this dark sector, offering scientists an unprecedented opportunity to study objects composed primarily of dark matter and to investigate potential interactions between dark matter and other unknown forces. The discovery of even more exotic forms of dark matter could challenge our current understanding of particle physics and lead to new theories about the fundamental building blocks of the universe. The study of ultra-dark galaxies also highlights the need for cross-disciplinary research. As astronomers work to uncover the secrets of these galaxies, they are increasingly relying on the expertise of physicists, mathematicians, and computer scientists. Theoretical models of dark matter and galaxy formation must be constantly refined and tested against new data, and the development of sophisticated simulations is crucial for understanding the complex dynamics at play in ultra-dark galaxies. These simulations help scientists explore the potential behaviors of dark matter and predict how ultra-dark galaxies might evolve over time. This interdisciplinary approach is key to solving some of the most profound questions in modern science. As research progresses, the discovery of ultra-dark galaxies could also have practical applications beyond astrophysics. For instance, understanding the properties of dark matter could eventually lead to breakthroughs in energy generation, materials science, and quantum computing. While these potential applications may seem distant, history has shown that the pursuit of fundamental knowledge often leads to unexpected innovations. Just as the study of electromagnetism eventually gave rise to technologies like electricity and magnetism-based devices, the exploration of dark matter and ultra-dark galaxies could one day have far-reaching implications for our technological future. Looking further into the future, the study of ultra-dark galaxies might even change the way we think about the fundamental forces of the universe. Dark matter and dark energy are currently among the greatest mysteries in science, and understanding their nature could lead to the discovery of new laws of physics that govern the cosmos. If ultra-dark galaxies can reveal new properties of dark matter, or if we can find a way to directly interact with dark matter particles, it might challenge our understanding of the very nature of reality. In the context of the broader scientific narrative, ultra-dark galaxies are a reminder that the universe is not only much older and more complex than we can fully comprehend, but also much stranger. As our observational tools improve and our theories evolve, we are increasingly able to peer deeper into the cosmos and explore the hidden structures that govern the universe. These discoveries not only expand our knowledge of space but also push the boundaries of what is possible in science and technology. Ultra-dark galaxies are an invitation to explore the unknown and challenge the limits of human understanding. The mystery of ultra-dark galaxies is far from solved, and the journey to understand them is only beginning. These galaxies are not just a curiosity. They are a key piece of the cosmic puzzle that will help us answer some of the most fundamental questions in science. From their unique composition of dark matter to their implications for galaxy formation, the study of ultra-dark galaxies promises to reshape our understanding of the universe. As we continue to explore these fascinating structures, we will likely uncover even more profound and surprising discoveries that will challenge our perceptions of the cosmos and push the boundaries of human knowledge. As we continue our journey into the realm of ultra-dark galaxies, we begin to realize that these mysterious cosmic objects may hold the answers to some of the most significant and unresolved questions in astrophysics. What makes them truly fascinating is their potential to unlock new areas of research that go beyond the typical boundaries of conventional astronomy. These galaxies, composed largely of dark matter, could be the key to understanding not only the nature of dark matter itself but also the fundamental forces that govern the universe on the largest scales. One of the most pressing questions in modern cosmology is how dark matter interacts with ordinary matter. Dark matter, though invisible and undetectable by direct means, is thought to make up about 27% of the universe's total mass energy content. It doesn't emit, absorb, or reflect light, which makes it incredibly difficult to study. However, scientists have inferred its existence based on its gravitational effects on visible matter. This is where ultra-dark galaxies come into play. These galaxies are believed to be composed almost entirely of dark matter, with very few visible stars or other types of ordinary matter. Their gravitational effects, while subtle, offer a unique opportunity to study dark matter in its natural state, potentially revealing new insights into its properties and interactions. By analyzing the structure and behavior of ultra-dark galaxies, astronomers may be able to better understand how dark matter clumps together and how it influences galaxy formation. These galaxies could act as cosmic laboratories, offering clues about the fundamental nature of dark matter particles and the forces that govern their interactions. For instance, the way ultra-dark galaxies are shaped and distributed in the universe could tell us more about the dark matter's role in the early stages of the universe, potentially shedding light on how galaxies form and evolve over time. Ultra-dark galaxies also provide a unique perspective on the relationship between dark matter and other cosmic phenomena. In particular, these galaxies may help to clarify the mysterious connection between dark matter and the large-scale structure of the universe. Current models suggest that dark matter played a crucial role in the formation of cosmic structures, such as galaxy clusters and superclusters, by providing the gravitational pull necessary for the collapse of gas and dust into galaxies. However, the exact nature of this relationship remains elusive. Ultra-dark galaxies, with their dark matter-dominated composition, may offer key insights into how dark matter influences the growth and evolution of these structures over cosmic time. In addition to offering a glimpse into the nature of dark matter, ultra-dark galaxies also raise intriguing questions about the fundamental properties of light and gravity. Since these galaxies contain so little visible matter, their light emissions are often too faint to detect with traditional telescopes. However, the gravitational influence of these galaxies is still detectable, even from vast distances. By studying the way light bends around ultra-dark galaxies, a phenomenon known as gravitational lensing, astronomers can gain valuable information about the distribution of dark matter within these galaxies. This, in turn, can help us refine our understanding of how gravity behaves in dark matter-dominated environments. One of the most profound implications of studying ultra-dark galaxies is their potential to challenge our existing models of galaxy formation. Conventional theories of galaxy formation suggest that galaxies form through the collapse of gas and dust, which eventually condenses into stars and other visible objects. However, ultra-dark galaxies appear to have formed without the usual abundance of visible matter. This raises the possibility that there may be other, as yet undiscovered processes at work in the formation of galaxies. Perhaps ultra-dark galaxies are the result of a different type of collapse, one in which dark matter played a more dominant role in shaping their structure. This could lead to a paradigm shift in our understanding of how galaxies form and evolve, forcing us to reconsider the very mechanisms that govern the growth of cosmic structures. Moreover, the study of ultra-dark galaxies could have far-reaching implications for our understanding of the history and future of the universe. If ultra-dark galaxies are indeed the remnants of an early phase in cosmic evolution, their study could provide a glimpse into the conditions that existed in the early universe. These galaxies could serve as fossils of a time when dark matter was more dominant, offering a unique window into the state of the universe before the formation of stars and galaxies as we know them. This could help us understand the processes that led to the universe's current configuration and offer clues about the future evolution of cosmic structures. Ultra-dark galaxies could also provide critical insights into the future of dark matter research. For years, scientists have sought to detect dark matter particles directly in laboratories on Earth. While these efforts have yielded little success so far, the study of ultra-dark galaxies may offer a more natural way to observe the effects of dark matter on a cosmic scale. By understanding how dark matter behaves in these extreme environments, scientists may be able to devise new methods for detecting dark matter particles, bringing us one step closer to unlocking the secrets of the dark sector. In terms of technological advancements, the search for ultra-dark galaxies is pushing the limits of observational astronomy. The instruments needed to detect and study these faint, distant galaxies are some of the most sophisticated in the world. Telescopes like the Hubble Space Telescope, the James Webb Space Telescope, and the upcoming Vera C. Rubin Observatory are all playing critical roles in uncovering the secrets of the universe's darkest corners. These instruments allow scientists to observe distant galaxies with unprecedented detail, providing insights into the structure and composition of ultra-dark galaxies that were once thought to be beyond our reach. These advancements in technology are also enabling scientists to push the boundaries of our understanding of the universe in other ways. For example, new developments in gravitational wave astronomy are providing a fresh perspective on the universe's most mysterious objects. By studying the ripples in space-time caused by events like black hole mergers and supernova explosions, astronomers are gaining new insights into the fundamental nature of matter and energy. As these technologies continue to evolve, we can expect even more groundbreaking discoveries about the universe and the role that ultra-dark galaxies play in shaping its evolution. In the coming years, the study of ultra-dark galaxies will undoubtedly continue to be one of the most exciting areas of research in astrophysics. With each new discovery, scientists will uncover more about the nature of dark matter, galaxy formation, and the large-scale structure of the universe. As our knowledge deepens, we may find that the study of these enigmatic galaxies holds the key to some of the greatest mysteries in science, offering answers to questions that have puzzled astronomers for centuries. The mystery of ultra-dark galaxies is not just about understanding these strange and elusive objects. It is about understanding the very nature of the universe itself. As we delve deeper into the dark corners of the cosmos, we are constantly reminded of how much we still have to learn. Ultra-dark galaxies are not just a curiosity. They are a window into the deepest secrets of the universe, a challenge to our current models of physics and cosmology, and a beacon guiding us toward new frontiers of discovery. As we continue to explore the enigma of ultra-dark galaxies, it's essential to recognize how their study intersects with some of the most profound questions in astrophysics and cosmology. These galaxies, largely composed of dark matter, challenge our understanding of what it means for a galaxy to exist, how it evolves, and how it fits into the larger cosmic landscape. The mere existence of ultra-dark galaxies suggests that our models of galaxy formation may be far from complete. Traditionally, galaxies were thought to form through the gravitational collapse of gas, dust, and dark matter, with the visible matter, the stars and gas, forming at the center as gravity pulled everything together. Ultra-dark galaxies, however, appear to defy this pattern. Their lack of significant visible matter raises the question, could there be other ways that galaxies could form, especially in dark matter-dominated environments? To explore this, it's crucial to look at the properties of these ultra-dark galaxies in detail. While many of these galaxies were detected through their gravitational influence on nearby objects or through the bending of light, a phenomenon called gravitational lensing, others have been identified through their faint or entirely absent emission of light. In some cases, ultra-dark galaxies are observed as dark halos around larger galaxies. The dominant material in these halos appears to be dark matter, but there is almost no visible matter in the form of stars, gas, or dust. This stark absence of visible matter places them in a category that's truly unique and mysterious, raising questions about the mechanisms at work behind their formation and structure. The key challenge in studying these galaxies is that they are incredibly difficult to detect. Since they emit little to no light, scientists must rely on indirect methods to identify their existence. Gravitational lensing, as mentioned earlier, is one such method. When light from a more distant object, such as a quasar, passes through the gravitational field of a dark galaxy, the path of the light is bent. This can produce a distorted image of the object, which can be observed by telescopes. By studying these distortions, astronomers can infer the presence of dark matter and gain insight into the distribution of mass within the galaxy. In some cases, scientists have detected ultra-dark galaxies through the effects they have on the motion of nearby galaxies or through their impact on the cosmic microwave background radiation, the faint afterglow of the Big Bang. This reliance on indirect observation forces astronomers to rethink traditional methods of studying galaxies. Unlike typical galaxies, which can be observed in visible, infrared, or radio wavelengths, ultra-dark galaxies require more creative methods to detect. As technology continues to advance, future telescopes and observatories will likely improve our ability to identify these elusive galaxies with greater accuracy. The upcoming space telescopes, like the James Webb Space Telescope, will be critical in this effort, as they are designed to capture light across a broad spectrum of wavelengths, including those that are otherwise difficult to observe from Earth's surface. This may allow us to peer deeper into the universe and uncover more ultra-dark galaxies that have remained hidden from view for so long. One of the most exciting possibilities that comes from the discovery of ultra-dark galaxies is the chance to study the properties of dark matter in detail. While we can't observe dark matter directly, its presence is inferred through its gravitational effects on visible matter. By studying the way dark matter interacts with other types of matter in ultra-dark galaxies, astronomers may be able to reveal new properties of this mysterious substance. For instance, one question that has puzzled scientists for decades is whether dark matter is made up of particles that are fundamentally different from the ordinary particles that make up the visible universe. Currently, dark matter is thought to consist of weakly interacting massive particles, WIMPs, though other theories propose that it could be made up of axions or sterile neutrinos. The study of ultra-dark galaxies could provide valuable clues to help resolve this question, as these galaxies offer a unique environment where dark matter dominates. These galaxies may also help us understand the role that dark matter played in the formation of the first galaxies. The early universe was a very different place, with the first galaxies forming from clouds of gas and dark matter that gradually clumped together due to gravitational attraction. However, the exact details of this process remain uncertain. Some researchers speculate that ultra-dark galaxies could be remnants of the very first galaxies to form, offering a glimpse into a time when dark matter was more dominant than it is today. These galaxies could be the key to understanding how the first structures in the universe took shape and how dark matter influenced the growth of the earliest cosmic objects. The discovery of ultra-dark galaxies also raises the question of how common these objects are. If ultra-dark galaxies are indeed a normal part of the cosmic landscape, it could significantly alter our understanding of galaxy formation and evolution. In some cases, these galaxies could be remnants of an earlier phase of the universe, while in other instances, they might represent an entirely new mode of galaxy formation. Their discovery challenges the notion that all galaxies must be composed of a significant amount of visible matter. Instead, it suggests that the universe may harbor a much wider variety of galaxies than previously imagined, many of which are hidden in the depths of space. Furthermore, ultra-dark galaxies may provide us with critical insights into the long-term evolution of the universe. Since dark matter plays such a crucial role in shaping the formation and growth of cosmic structures, understanding how ultra-dark galaxies evolve over time could shed light on the future of the universe itself. Will these galaxies eventually light up as visible matter accumulates, or will they remain dark for all eternity? Will the dark matter in these galaxies ever interact with ordinary matter in a way that allows the formation of stars, or will they remain frozen in a state of stasis? The answers to these questions could have profound implications for our understanding of the ultimate fate of the universe. In essence, the study of ultra-dark galaxies serves as a reminder of how much we have yet to learn about the cosmos. These galaxies are not just a curiosity, they are a key that could unlock many of the greatest mysteries of the universe. By studying their structure, behavior, and interactions with dark matter, we may be able to answer questions that have eluded scientists for centuries. How did the universe form? What is dark matter? And how does it influence the behavior of galaxies and other cosmic structures? How do galaxies evolve, and what role does dark matter play in their growth? Each new discovery in the field of ultra-dark galaxies takes us one step closer to answering these questions. As we continue to probe deeper into the cosmos, we are constantly reminded of how much we have yet to uncover. Ultra-dark galaxies represent the frontier of our understanding of the universe, offering us a glimpse into a mysterious and dark realm that has remained hidden from view for so long. Whether these galaxies are remnants of an ancient past or harbingers of a new era in cosmic evolution, they are bound to remain a source of fascination for astronomers and astrophysicists for years to come. As we continue to explore the mysteries surrounding ultra-dark galaxies, it's essential to ask whether these galaxies are merely isolated oddities or if they represent a more fundamental aspect of the cosmos. One crucial question that arises is whether they could help explain some of the unexplained phenomena we observe throughout the universe. For instance, ultra-dark galaxies might offer new insights into the so-called missing matter problem, which has puzzled astrophysicists for decades. This problem refers to the discrepancy between the amount of visible matter we can observe in the universe and the amount of mass that we know must exist to account for the gravitational effects we observe. The idea that dark matter could account for this missing mass has been widely accepted, but the detailed nature of this matter remains elusive. Ultra-dark galaxies, with their distinct lack of visible matter, could serve as a natural laboratory to study how dark matter interacts with regular matter. In many ways, ultra-dark galaxies are like cosmic laboratories that allow us to test various hypotheses about the nature of the universe, dark matter, and even dark energy. These galaxies, though rare, provide researchers with invaluable opportunities to refine models of galaxy formation, the growth of large-scale structures, and the evolution of the universe itself. The study of these galaxies helps us better understand the boundaries of known physics, offering the potential for groundbreaking discoveries that could reshape our entire view of cosmology. The search for ultra-dark galaxies also brings to light the limitations of current observational techniques. Even the most advanced telescopes and observatories face challenges when trying to detect and study these galaxies. While gravitational lensing remains one of the primary methods of detection, it requires a series of fortunate circumstances for it to work effectively. The ultra-dark galaxy must align with a background object whose light can be bent by the galaxy's gravitational field. This is a rare occurrence, and means that our ability to identify ultra-dark galaxies is still relatively limited. Furthermore, because these galaxies emit so little light, they are practically invisible to conventional astronomical surveys. As a result, our understanding of how many ultra-dark galaxies might exist and how they fit into the larger cosmic framework is still incomplete. As technology progresses, however, there is hope that the detection of these galaxies will become more routine. Advanced space telescopes, such as the James Webb Space Telescope, offer a new frontier in the quest to uncover hidden cosmic structures. These telescopes are designed to observe in infrared wavelengths, allowing them to see through the dust and gas that obscure many objects in the universe. As our observational capabilities improve, we may find that ultra-dark galaxies are more common than previously thought. If this turns out to be the case, it would fundamentally alter our understanding of how galaxies form and evolve. At the same time, the study of ultra-dark galaxies might also help us probe deeper into the very fabric of the universe. One of the most exciting aspects of dark matter is that it is believed to interact primarily through gravity and possibly through weak nuclear forces, but it doesn't interact electromagnetically. This means that dark matter doesn't emit, absorb, or reflect light, making it invisible to conventional observation methods. However, if ultra-dark galaxies are composed largely of dark matter, studying how they behave can shed light on how this mysterious substance works. For example, if dark matter affects the formation and behavior of galaxies in a way that is not currently understood, ultra-dark galaxies may provide a glimpse into this process. Moreover, ultra-dark galaxies may offer clues to the ultimate fate of the universe. We know that the universe is expanding, but what drives this expansion? Some theories suggest that dark energy, another mysterious and largely uncharted force, could be responsible for accelerating this expansion. Dark energy, like dark matter, is one of the most significant and perplexing elements in cosmology. If ultra-dark galaxies are found to be common in the distant universe, their study could provide critical clues to understanding the relationship between dark matter, dark energy, and the expansion of the universe. Could ultra-dark galaxies be the remnants of an earlier, slower era in the universe, frozen in time as the cosmic expansion continued to accelerate? Or, conversely, could they be a product of the universe's current accelerated expansion? The study of ultra-dark galaxies also touches upon the broader search for dark matter in the universe. Dark matter, which is believed to make up about 27% of the total mass and energy content of the universe, is one of the most pressing mysteries in modern science. Its elusive nature has led to the development of many different theories about what it might be. Some of the leading candidates include weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. The exact nature of dark matter remains a mystery, and ultra-dark galaxies could help narrow down the possibilities. By observing how dark matter behaves in these galaxies, researchers can refine their models and gain new insights into the properties of dark matter itself. What makes the study of ultra-dark galaxies even more intriguing is their potential connection to the evolution of galaxy clusters. Galaxy clusters, which are some of the largest gravitationally bound structures in the universe, are primarily made up of galaxies, gas, and dark matter. In many ways, the study of dark matter in galaxy clusters has been one of the key methods for understanding how dark matter behaves on a large scale. Ultra-dark galaxies, with their peculiar lack of visible matter, could offer insights into the role of dark matter in the formation and evolution of galaxy clusters. If ultra-dark galaxies are found to be present in these massive structures, it could suggest that dark matter plays an even more dominant role in galaxy formation than previously thought. Another fascinating aspect of ultra-dark galaxies is their potential connection to the so-called first galaxies that formed after the Big Bang. The early universe was a very different place from the universe we know today, and galaxies were much smaller and less evolved. Many of the earliest galaxies were likely dominated by dark matter, with only small amounts of visible matter present. Ultra-dark galaxies could be the remnants of these first galaxies, offering a window into the distant past of the cosmos. If this is the case, ultra-dark galaxies could help us answer fundamental questions about the earliest stages of galaxy formation and the role of dark matter in this process. As we continue to study these fascinating objects, it's becoming increasingly clear that ultra-dark galaxies are not just a curiosity. They are an essential piece of the puzzle when it comes to understanding the universe. By studying them, we may unlock the secrets of dark matter, galaxy formation, and the evolution of cosmic structures. The mystery of ultra-dark galaxies may one day be solved, but for now, they remain one of the most intriguing and enigmatic aspects of the universe, waiting for us to uncover their secrets. Continuing the investigation into ultra-dark galaxies, we must also consider the broader implications of their discovery for our understanding of the entire cosmos. Ultra-dark galaxies aren't just strange, isolated objects. They could help explain some of the most fundamental mysteries of the universe, including the nature of dark matter, the formation of galaxies, and the future trajectory of cosmic expansion. One of the significant implications of ultra-dark galaxies is how they might influence the formation of more typical galaxies. Our own galaxy, the Milky Way, is primarily composed of regular matter like stars, gas, and dust, with a substantial amount of dark matter that helps bind it together. The discovery of ultra-dark galaxies could offer a different perspective on the ways in which galaxies evolve over time. Could it be that ultra-dark galaxies represent an early stage of galaxy formation, or might they be the result of a process that bypasses the usual steps we observe in more typical galaxies? Could they have formed by unusual or extreme conditions in the early universe, offering insights into processes that we might not yet fully understand? Ultra-dark galaxies might also have profound implications for our understanding of the cold dark matter hypothesis. Cold dark matter is a leading theory that posits that dark matter particles move slowly relative to the speed of light. This theory suggests that dark matter doesn't interact much with regular matter, except through gravity. If ultra-dark galaxies are composed predominantly of dark matter, it could lend further support to this theory. It's possible that these galaxies are not simply rare outliers but instead represent a more common type of structure that is hidden from our current observational capabilities. This would change how we think about the distribution of dark matter across the universe, pushing us to rethink the standard models of cosmology. Furthermore, ultra-dark galaxies may provide valuable insights into the history of galaxy mergers. Galaxy mergers are a known phenomenon in the universe, where two or more galaxies collide and combine to form a new, larger galaxy. These events are thought to play a crucial role in shaping the properties of galaxies, including their size, shape, and overall composition. Ultra-dark galaxies could be the remnants of mergers that led to the stripping away of visible matter, leaving behind a core composed mostly of dark matter. By studying these galaxies, we could learn more about the processes that take place during these dramatic cosmic events and how they influence the evolution of galaxies over time. The interaction between dark matter and regular matter in ultra-dark galaxies could also offer a unique opportunity to test current cosmological models. In the standard model of cosmology, dark matter is thought to play a key role in the formation of galaxies and large-scale structures in the universe. However, the exact nature of this interaction is still not fully understood. Ultra-dark galaxies, with their apparent lack of visible matter, could serve as a natural experiment that challenges or confirms the predictions of these models. For instance, if we find that these galaxies are able to hold together despite the absence of visible matter, it would provide strong evidence that dark matter behaves differently than we currently understand. In addition to the scientific implications, the study of ultra-dark galaxies could have philosophical ramifications for our understanding of the universe and our place within it. The very existence of such mysterious and elusive objects forces us to confront the limits of human knowledge and our ability to comprehend the cosmos. For centuries, astronomers and cosmologists have worked to uncover the fundamental laws that govern the universe. But discoveries like ultradark galaxies remind us that there are still vast unknowns to explore. In many ways, they challenge our assumptions about what is possible in the universe and push us to expand the boundaries of scientific inquiry. In a sense, the mystery of ultradark galaxies is a symbol of the broader quest for knowledge. Just as these galaxies are hidden from view, so too are many other mysteries of the universe obscured by the limitations of our current technology and understanding. However, as we continue to develop new tools and techniques for observing the cosmos, we open up the possibility of uncovering these hidden secrets. The discovery of ultradark galaxies is just one step in this ongoing journey of exploration, but it holds the potential to unlock a wealth of new knowledge about the nature of the universe. Another fascinating aspect of ultradark galaxies is their potential role in the end stages of galaxy evolution. While much of the focus in cosmology has been on the birth and growth of galaxies, researchers are also increasingly interested in how galaxies evolve over time and eventually die. Ultra-dark galaxies could represent a late stage in the life cycle of galaxies, where most of the visible matter has been stripped away, leaving only dark matter behind. This would make them an important piece of the puzzle when it comes to understanding the life cycle of galaxies, from their formation to their eventual demise. One intriguing possibility is that ultra-dark galaxies could be the result of a process called feedback, in which large, central black holes or other energetic phenomena strip away the gas and dust from a galaxy, leaving only its dark matter behind. If this hypothesis proves to be true, it could revolutionize our understanding of how galaxies evolve and die. It would suggest that dark matter plays an even more central role in the life cycle of galaxies than previously thought, possibly affecting how galaxies form, grow, and ultimately dissolve into nothing. The study of ultra-dark galaxies could also help us answer some of the biggest questions in astrophysics. For example, one of the key questions in cosmology is why the universe is structured the way it is. Why do galaxies form in clusters? Why do they appear to follow certain patterns in their distribution across the cosmos? By studying ultra-dark galaxies, we might gain insights into these fundamental questions. If these galaxies are somehow connected to the larger cosmic web, they could help us better understand the forces that shape the universe on the largest scales. Moreover, ultra-dark galaxies might also be key to understanding the relationship between dark matter and dark energy. Dark matter and dark energy are two of the most profound mysteries in modern science. While we know that dark matter has mass and interacts gravitationally with visible matter, dark energy appears to drive the accelerated expansion of the universe. Could ultra-dark galaxies be some sort of bridge between these two enigmatic forces? Their study might provide clues about how dark matter and dark energy interact, and what role they play in the evolution of the universe. As we continue to refine our understanding of these extraordinary galaxies, it's clear that ultra-dark galaxies are not just isolated oddities. They are a window into a deeper understanding of the universe. By studying them, we are not only unraveling the mysteries of dark matter and galaxy formation but also gaining new insights into the fundamental nature of the cosmos itself. These galaxies remind us that the universe is far more complex and mysterious than we can even begin to imagine, and that the pursuit of knowledge is an ongoing journey that requires both curiosity and persistence. The more we uncover about ultra-dark galaxies, the more we realize how much more there is still to discover. And perhaps, in the end, these enigmatic objects will help us answer some of the most profound questions that have fascinated humanity for millennia. As we continue to peel back the layers of mystery surrounding ultra-dark galaxies, we begin to recognize that their study is far more than just an academic exercise. These galaxies might represent a crucial turning point in our understanding of the universe, challenging everything we thought we knew about cosmic formation, structure, and the very fabric of reality itself. With their bizarre makeup and mysterious properties, ultra-dark galaxies beckon us to explore new frontiers of science and technology. One of the most intriguing aspects of ultra-dark galaxies is their potential to revolutionize our understanding of the missing mass problem. As far as we know, roughly 85% of the mass in the universe is made up of dark matter, yet its exact nature has remained elusive. It does not emit light, nor does it interact in any meaningful way with regular matter, except through gravity. For years, scientists have been trying to detect and study dark matter, but it remains one of the most stubborn and elusive components of the universe. However, ultra-dark galaxies, with their distinct absence of visible matter, could be the key to unlocking the secrets of dark matter once and for all. The dark matter that makes up ultra-dark galaxies likely interacts with normal matter only via gravity, but because it's so predominant in these galaxies, it could reveal clues about the fundamental properties of dark matter itself. Perhaps we need a new theoretical framework to understand how dark matter behaves in extreme environments. These ultra-dark galaxies might serve as a natural laboratory, providing us with the opportunity to test hypotheses about dark matter in ways that were previously impossible. In addition to dark matter, Ultra-dark galaxies may also help clarify the relationship between dark matter and galaxy formation. In most galaxies, including the Milky Way, dark matter is thought to be a stabilizing force, keeping stars in orbit around the galactic center. The fact that ultra-dark galaxies exist in such strange configurations suggests that the rules we currently use to model galaxy formation may not fully account for the complexity of how dark matter and visible matter interact. Ultra-dark galaxies might point to a different form of galaxy evolution that we've yet to fully understand, one where the dark matter plays an even more dominant role than we previously thought. But what do these discoveries mean for the way we understand the history of the universe? If ultra-dark galaxies were present in the early stages of the cosmos, it could mean that our models of how galaxies form are incomplete. Perhaps these galaxies were some of the first to form in the universe, made primarily of dark matter, with visible stars and gas being stripped away over time. The study of these galaxies might allow us to peer back in time to witness the formation of the very first galaxies, offering clues about how the universe transitioned from its primordial state to the structured, star-filled cosmos we see today. It might also help us understand the timeline of dark matter's role in galactic evolution, providing a more complete picture of cosmic history. We should also consider how ultra-dark galaxies might fit into the larger structure of the universe itself. One of the most significant revelations of modern cosmology is the discovery of the cosmic web, a vast, interconnected network of galaxies and dark matter that forms the largest structure in the known universe. This web stretches across billions of light-years, with galaxies clustered along filament-like structures, while dark matter acts as the scaffolding that holds it all together. Ultra-dark galaxies, by virtue of their strange composition, could provide new insights into how dark matter influences the formation of cosmic structures. They could be key players in helping to map out the large-scale structure of the universe, providing a glimpse into the role of dark matter in organizing the cosmos on the grandest scales. Moreover, ultra-dark galaxies could also help us refine our understanding of the expansion of the universe. One of the biggest questions in cosmology is how the universe is expanding and whether its expansion is accelerating or decelerating over time. Dark energy, the mysterious force believed to be driving the accelerated expansion, has been a major focus of research in recent decades. However, it's still unclear how dark energy interacts with galaxies and cosmic structures. Ultra-dark galaxies, with their peculiar nature, might provide a unique perspective on this issue. If dark matter is influencing the formation of these galaxies, and dark energy is accelerating the expansion of the universe, then ultra-dark galaxies could represent an intersection of these two forces, helping to shed light on how they interact and influence one another. In addition to the questions about dark matter and dark energy, ultra-dark galaxies might also provide insight into the behavior of galaxy clusters. Most of the galaxies we observe are part of larger clusters, bound together by gravity. These clusters range in size from small groups of a few galaxies to massive collections containing thousands of galaxies. Ultra-dark galaxies might behave differently within these clusters, potentially revealing new information about how galaxies interact with one another in such environments. For instance, could ultra-dark galaxies be more likely to survive in certain types of galaxy clusters, where the gravitational forces are extreme and dark matter can play a stronger role in holding them together? Or do ultra-dark galaxies prefer more isolated environments, where they can exist with minimal interaction from other galaxies? These questions are key to understanding the dynamics of galaxy clusters and the larger structure of the universe. Furthermore, the discovery of ultra-dark galaxies might help answer some of the most profound philosophical questions about the universe. For centuries, humans have gazed up at the stars, wondering about the nature of the cosmos and our place within it. As we discover more about the hidden realms of dark matter, dark energy, and ultra-dark galaxies, we are forced to confront the fact that the universe is far more complex than we could have ever imagined. The mysteries surrounding ultra-dark galaxies might not only shape the future of astrophysics, but could also force us to reevaluate our entire understanding of existence. If these galaxies reveal the true nature of dark matter, or even offer clues about the structure of the cosmos at the largest scales, they could challenge our perceptions of space, time, and reality itself. This deeper understanding could ultimately have profound implications for the future of humanity. As we continue to explore the mysteries of the universe, we might uncover technologies and knowledge that could help us solve some of the biggest challenges we face here on Earth. For example, understanding dark matter could lead to breakthroughs in energy production, transportation, and materials science. As we learn more about how the universe operates on the most fundamental levels, we might uncover new ways to harness the forces of nature for the benefit of all. Ultra-dark galaxies, though mysterious, are a symbol of the potential for discovery and the endless possibilities that await us as we continue to explore the cosmos. To summarize, the mystery of ultra-dark galaxies is not just a scientific curiosity, it is a profound challenge to everything we know about the universe. These galaxies, composed almost entirely of dark matter, hold the potential to unlock answers to some of the most fundamental questions in cosmology. By studying ultra-dark galaxies, we can learn more about dark matter, galaxy formation, the structure of the universe, and even the nature of reality itself. As our tools and techniques for observing the cosmos continue to improve, we may find that ultra-dark galaxies are just the beginning of a new era of discovery, one that promises to reshape our understanding of the universe and our place within it. The story of ultra-dark galaxies is far from over, and as we continue to explore and study these enigmatic objects, we are sure to uncover even more mysteries. Who knows what secrets they might reveal, or what new questions they might pose? One thing is certain, the study of ultra-dark galaxies is a key that could unlock the doors to some of the greatest mysteries of the universe, and in doing so, it might change the way we look at the cosmos forever. The possibilities surrounding ultra-dark galaxies are as vast as the mysteries they present. We have only scratched the surface, and each new discovery about these elusive galaxies could bring us closer to answering questions that have remained unsolved for centuries. As researchers push the boundaries of technology, new observations and theoretical breakthroughs are expected, adding layers of complexity to our understanding of these fascinating cosmic objects. The more we learn, the more we realize that ultra-dark galaxies may be one of the most significant puzzles in modern astrophysics, with the potential to redefine our place in the universe. One of the key challenges in studying ultra-dark galaxies is their extreme scarcity. These galaxies are so rare that finding one is akin to stumbling upon a hidden treasure in the vastness of space. Even with powerful telescopes and advanced imaging techniques, ultra-dark galaxies are difficult to spot because they emit little to no light. Their invisibility makes them nearly impossible to study using traditional methods, which typically rely on visible light or other electromagnetic radiation to identify celestial objects. This has led scientists to employ more creative approaches to uncover these enigmatic galaxies, such as looking for them in the faint gravitational effects they have on nearby objects, or detecting their presence through the behavior of cosmic gas. Gravitational lensing, a phenomenon where light from distant objects is bent by the gravitational influence of massive objects between the source and the observer, has proven to be one of the most effective tools in the search for ultra-dark galaxies. When a large mass, such as a galaxy or cluster of galaxies, bends the light from a more distant object, it creates a distorted image of the background source. This can allow scientists to observe galaxies that would otherwise be hidden from view. Ultra-dark galaxies, with their massive dark matter halos, may be detected through this method, as their gravitational influence could distort light from more distant sources in unique ways. By carefully analyzing these distortions, astronomers may be able to infer the presence of ultra-dark galaxies and study their properties in greater detail. In addition to gravitational lensing, scientists are also turning to other forms of observation to uncover the secrets of ultra-dark galaxies. One promising approach is to look for the faint radiation emitted by dark matter itself. While dark matter does not interact with light in the same way that normal matter does, there is still the possibility that it may produce very weak emissions in certain conditions. These emissions could be detectable using specialized instruments, such as those designed to detect high-energy photons or cosmic rays. If such signals can be identified, they could provide a direct link to dark matter and offer valuable insights into the nature of ultra-dark galaxies. Moreover, the discovery of ultra-dark galaxies could have profound implications for the field of cosmology. These galaxies might represent a missing piece in our current models of how galaxies evolve and interact with one another. Traditionally, galaxies have been thought to form through the collapse of gas and dust under the influence of gravity, with stars and other visible matter making up the bulk of the galaxy's mass. However, the existence of ultra-dark galaxies challenges this picture, suggesting that dark matter could play a much larger role in galaxy formation than previously believed. If dark matter is capable of forming entire galaxies on its own, this could rewrite our understanding of the forces that govern cosmic evolution. Furthermore, ultra-dark galaxies might provide new insights into the relationship between normal matter and dark matter. Most galaxies, including our own, contain both visible matter, such as stars, gas, and dust, and invisible dark matter, which forms a halo around the galaxy and provides the gravitational pull needed to keep the galaxy intact. In contrast, ultra-dark galaxies are made up almost entirely of dark matter, with very little visible matter. This stark contrast raises important questions about how dark matter and visible matter interact in different environments. If dark matter can form galaxies without the need for visible stars and gas, it could imply that our current understanding of galaxy formation is incomplete, and that dark matter may have far more influence on the structure of the universe than we once thought. In this context, the discovery of ultra-dark galaxies is not only a breakthrough in the study of dark matter but also a potential window into the mysteries of galaxy formation. These galaxies could represent a primordial stage in galactic evolution, offering clues about how the first galaxies in the universe may have formed. By studying their properties and behavior, astronomers could learn more about the conditions that existed in the early universe and how dark matter may have played a role in shaping the cosmos. Moreover, ultra-dark galaxies could challenge our understanding of the ultimate fate of galaxies. In most galaxies, stars form from the collapse of gas clouds, and over time, these stars burn out and die, eventually leading to the death of the galaxy itself. However, in ultra-dark galaxies, where visible matter is scarce, the processes that govern star formation and galaxy evolution might be fundamentally different. It's possible that these galaxies could live far longer than their more traditional counterparts, existing as dark matter-dominated systems that continue to evolve in ways we have yet to fully understand. This raises profound questions about the life cycle of galaxies and the potential for new forms of cosmic evolution. While much of the research surrounding ultra-dark galaxies is still in its early stages, it is clear that they hold the key to answering some of the most fundamental questions in cosmology. As our tools for exploring the universe become more sophisticated, we can expect to uncover more about these strange and elusive objects. With each new discovery, we will gain a deeper understanding of dark matter, galaxy formation, and the evolution of the universe itself. And as we continue to push the boundaries of our knowledge, ultra-dark galaxies may one day help us unlock some of the greatest mysteries of all. What is dark matter? How did the universe come to be? And perhaps most importantly, are we truly alone in the cosmos? The journey to understand ultra-dark galaxies is far from over. As we look deeper into the universe and refine our methods of observation, we are sure to uncover even more surprising discoveries. The study of these galaxies is not just about unraveling the mysteries of dark matter or understanding the history of the universe. It is also about pushing the limits of human knowledge and venturing into realms of science that were once thought to be beyond our reach. The mysteries of ultra-dark galaxies will undoubtedly continue to captivate the imagination of scientists and the public alike for years to come, offering a tantalizing glimpse into a universe that is far more complex and mysterious than we could ever have imagined. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.